Okay, so we've shown one form of insert using an iterator to specify one value to be inserted, and we've seen one form of erase where you specify an iterator indicating which value you want to erase. There are overloaded versions of these insert and erase functions. For example, here we have a slightly different version of insert that again takes an iterator where you want to do your inserting as the first argument, but this time we've specified two arguments. The second argument after the iterator is a count of the number of values that you want to insert. So here we're indicating that after the end of the vector we want to insert two values. And the third argument is the value that you want to insert, in this case twice. So the upshot is, if we insert two 5s ahead of the end iterator, we're going to end up with 5 inserted twice following the 7. Now remember that end is one past the final element, so end is one past the 7, and we're inserting two 5s ahead of the end, which puts those 5s after the 7. Now you can step all iterators of all of the standard container types ahead one position by using the increment on the iterator. So ++it will always work for any kind of containers iterator. For a vector, you can use the +get symbol to move the iterator forward by several positions. Okay, so if I reset it to point to the beginning of the vector, that is to point to the -4, and then I add 3, well, now it is going to be pointing at the 9. Okay, so this was simply some examples of declaring and manipulating an iterator, and also using iterators to insert values and erase values within the vector. So in the rest of this lecture, we're going to do an overview of what's called the C++ standard template library. This consists of 3 major components, and all of this is related to what's called generic programming. First of all, we have a large collection of different container types, namely sequence containers like vector and list, which, as we've seen, have order n search times. Also associative containers, such as sets and maps, which, as we've seen, have order log n search times. And unordered or hash table containers offering order 1 search times. In addition to those 3 categories of containers, there are some of what are called adapters that we talked about in FC1, namely stack, queue, and priority queue. Now, in order to make it convenient to traverse through containers and manipulate objects or collections of objects within containers, we make use of iterators. We've only been looking at what are called forward iterators, where we start from the beginning of a container and work our way forward. But it turns out there are other kinds of iterators as well. And there are also, it turns out, about 80 different standard algorithms that you can perform on containers using iterators. And you can also, of course, define your own generic algorithms that make use of iterators to step through and manipulate the contents of containers. Algorithms will come up in our next lecture. For this lecture, we're going to look at containers and more about iterators. This is by far the longest lecture in the course. We're going to talk about many categories of facilities that containers and iterators provide, but it's nothing close to covering everything, even though it may seem like a bit much to swallow. Okay, so any of the STL containers contains copies of objects and offers member functions and algorithms for manipulating copies of those objects. So that implies that you cannot have a container if the container does not have a public copy constructor. For example, we could not have a vector of employee objects because we cannot make a copy of an employee. It doesn't make sense to have 2 clones of one employee walking around. So A class that does not have a public copy constructor cannot be stored in a container. Likewise, you cannot have a container of references to objects, because a reference is simply an alternate name for an object. A reference itself is not an object. Now, you can certainly have containers of pointers to objects, and so although you cannot have a container of employees, you could certainly have a container such as a vector or a list or a set of pointers to employees. That'll work just fine. So here on slides 14 and 15 are the 5 sequence containers that the standard template library provides. And we're already familiar with a few of these. The vector container is described by the vector header, and the vector container makes it very efficient to insert and delete values only at the end. So there is, for the vector class, a push back function, but there is not a push front function. Being able to push a value at the front of a vector would be expensive. It would entail moving all of the values and all of the other elements in the vector one place further along in memory, which is a time-consuming operation. Now, you may complain that, well, look, didn't I just tell you about the insert and erase member functions that vector provides? And indeed, insert and erase are member functions that vector provides, but they do have somewhat complicated interfaces, and they do involve fussing around with iterators. And so that's intended to be a hint to someone using the vector class that although it's possible to do these facilities, it's not necessarily cheap in terms of time or memory. Okay, so we do not have a push front operation for a vector, but we can, if we're willing to suffer the expense, accomplish the same thing by doing an insert at the beginning of the vector of a value. Vectors offer convenient random access. That is, you can use the square bracket notation to subscript any element within the vector object. You can also traverse back and forth using iterators with plus plus to go forward or minus minus to go backward. Somewhat similar to a vector, but both a little less efficient and also a little more flexible, is the deck, or so-called double-ended queue. Now, a deck provides random access just like a vector does. That is, you can use square brackets to access an element within a deck, and you can increment your iterators both forward and backward. However, a deck internally is going to have gaps in it. A deck is sort of like a list of vectors chained together. And so it's not true for a deck that the elements are guaranteed to be in ascending contiguous memory. So that's a little less efficient than a vector, but on the other hand, a little more flexible, because not only can you cheaply push values at the back of a deck, but you can also very cheaply push values at the front of a deck as well. So if you want something like a vector, but you need to be able to conveniently and pretty efficiently manipulate things at the front of the container as well as at the back of the container, a deck is a good compromise. A list, which is implemented as a doubly linked list, is very efficient for inserting and deleting anywhere within the list, not just at the beginning and the end, but also anywhere in the middle that you want, because a list is implemented as a doubly linked list of individual elements. Inserting values into a list anywhere does not require you to move around the existing values within the list. Likewise, erasing an element or a sequence of elements from the list does not require you to move around in memory any of the remaining elements within the list. All right, so we do have efficient push back and we do have efficient push front. A list is not random access. That is, you can't do subscripting, but you can move iterators bidirectionally. That is, you can traverse through the list forward with plus plus or backward with minus minus. Okay, so if you need inserting and deleting to be very efficient operations, and you're willing to sacrifice not being able to do subscripting, then a list is going to be preferable to something like a vector or a deck.